Okay, let's start. Welcome to the week 11th of this classical mechanics course. So, this is the penultimate week, and hope you have been keeping up with the content. Before I start, I'd like to make announcements. Uh, One is that uh, if you need a special class, there is an option for that. I received an email from NPTEL team asking me to ask you guys basically if you want a special class on problem solving, or as I was thinking, on non-linear dynamics, which is like my bread and butter, and it's very trendy nowadays. And because it's an extension of this course, so obviously it's an extension of classical mechanics. Obviously, it's a course in itself and a lot difficult than this course. But what I can do is give a preview in an hour or two to give you kind of flavors of what can be done ahead. Another extension, by the way, of classical mechanics is quantum mechanics. You can go from classical to quantum. We'll learn about Poisson brackets, etc. in the next week. So through that, after quantizing, you get to quantum mechanics. That is also a possible direction. Okay, so I don't think people would be interested in this. Nevertheless, I mentioned this. In case you are interested, please tell me after the class, or you can write me an email. You know my email. In case you don't, it's arshchotelya@iitb.ac.in, or you can just type it in the YouTube chat box in case you are watching on YouTube. Oh, by the way, I should also mention that there are many people who are watching it on YouTube, and in fact, my subscriber count got multiplied by 13. It was 1 and now it's 13. So thank you very much. And the second thing is about feedback of these sessions. I would very much appreciate if you have any feedback, positive, negative, critical, anything. Okay, so if you have, you can just let me know. You can also give it on the portal itself. It appears there is an option for that. So that would be useful for me and the NPTEL people also, because they also want to make sure that quality of these sessions is on par. Okay, that said, so second was feedback. Let's begin by a quick recap of things. So this week we talked about tensors, then Hamiltonian equation of motion, and what was the last part? Ah, Liouville theorem. Okay, so starting with tensors, first we defined what a vector is. Definition of a vector. As they say, if you want to know which grade a student is, and you can't ask them, you can ask them a definition of this and that. For example, you can ask the definition of momentum. If they say they don't know, they are below class 8. If they say it's mass times velocity, they are in 8 to 10th grade or something. Then as they go above and
Sorry,
above,
your
yeah.
screen is not visible, sir.
Oh, screen is not visible. Oh, thank you for
Thank you, sir.
telling. Oh, Harish says please organize lecture on nonlinear dynamics. Okay, then I'll organize one class of possibly 2 hours. Thanks. Okay, okay. So since it was not visible, as I mentioned, uh, so I made two announcements, uh, one for special class and one for feedback. And so what I was talking about is if you ask for definition of momentum, you start with mass times velocity. Then you learn quantum mechanics, then you say it's the expectation value of this operator minus I h cross del by del x. Then when you learn classical mechanics, you say that yeah, it's the derivative of Hamiltonian with respect to the velocity qk dot, right? So there are many definitions. In the same way, the vector definition of a vector also varies with where you are on the academic stair. Okay, so the definition that we now have learned is that the components should change according to rotational matrix. Rotation matrix. So we know that R prime is some matrix A times R, and this is our rotational matrix. Okay, so in component form, it becomes xi prime is aij xj. Okay, so if your components change according to this rule, then you say it's a vector. Okay, so what is not a vector? For example, from this we can say delta x is vector, the displacement, which means the velocity is also vector, which means acceleration is vector, which means force is vector, and also you can say that x cross y is vector. Okay, if x and y are vector, etc., etc. So this would mean, by the way, that angular momentum is vector, torque is vector, etc. So anything physical that has a direction, that would be obviously a vector. What is not vector? So in high school, we learned that vector is a list of components. So if you have vector A, it's basically A1, A2, A3. And suppose this is a vector, which means it follows this rule. But suppose you uh, make another list of number which is square of these numbers, A2 square and A3 square. Now, is this a vector? Um, you can do additions of components, etc. Still, this is not a vector, because if you agree that these components transform according to the rule of this Aij, then these components will not, right? So now the definition of vector is that the rule itself becomes the definition. Okay, so then we say that a vector is just a special uh, type of object, and a general class of object is tensors. So vector is a one tensor or rank one tensor. So then you can ask, what is rank n tensor? An object. So we can say an object. Object as in a mathematical object that transforms as. Now if I have n components, right? So that should transform as, the prime should become a1 I a2 j etc. and this is I ag, right? So sorry, aij etc. whatever the number of indexes is. Okay, so it means the factor that is multiplied is this. And remember, it's not just a pure factor because these indices are being summed over. Okay, so there is a mixing of component, and that mixing should follow this rule. Okay. Um, then we said two important, two invariant tensors. First was delta ij, Kronecker delta matrix, and the second one is epsilon ijk, which is the antisymmetric Liouville symbol. And the definition for this was that epsilon 1, 2, 3 is equal to plus 1. So there are three rules. Second is that if two indices are equal, the component is 0. And third is exchanging two indices implies negative sign. So if it is plus 1 and you exchange two indices, it becomes minus 1. Actually, yeah, from this you can derive the second one. So basically there are only these two rules. And then you can show, as we did in the class, that when you transform it, all these rules are again followed, so the tensor remains the same. Okay, so and what can you do with tensors? You can do contraction. Okay, if you have that's a I j k times b lm, then this is a rank 5 tensor, right? But what you can do is contract say two indices with k and l and b lm. So now these two indices are summed over, so they do not appear in the final object, which would be something like c I j m. So rank 3. Okay, what we started was 3 plus 2 rank tensor. So because of this delta, we can get rid of 2 degrees, and so this is also called partial tracing, by the way. Okay, and yes, that is about it for tensors. Then we went to Hamiltonian. For that, the first concept was of legendary transformation. So what it says is that you start with any function f of x and you follow three rules blindly. Uh, First is consider another function that is another variable xi, and that function is given by xi minus f of x. Okay, so it's a function of both x and psi. And third is take derivative of this bigger capital F function with respect to x to 0, and that will give psi as a function of x, right? And that you can do easily. It is just f dash of x, right? And then you invert it, so x becomes some function of psi. Okay, and then you define a fourth function, sorry, third function, g of psi, which is just f, but evaluated at this value of x. So x is a function of psi and psi. So we can know the value of this f just by knowing the value of psi, because x depends on the psi. Okay, and is your is the Legendre transformation of f. Okay, so that is the definition, and the professor showed very nice example, which was half mx square. Okay, so and then the g of psi was psi square upon 2m, right? So as you can see, if x is treated as velocity, if x is velocity, then this is kinetic energy. Now, what is psi? Psi just becomes m times x, which is m times velocity. Remember, x is just a variable, it's not the position. So that is momentum. Okay, so this is again kinetic energy, but in a different form. So, and then we can just generalize if f of x. So let's say we have other functions also, f of x, x dot and t, which is just Lagrangian. Then your g of psi would be the Hamiltonian, x, p, and t, where p is your conjugate momentum, and then you can generalize this to multiple degrees of freedom. Okay, so the statement is Hamiltonian is Legendre transformation of our initial Lagrange. Okay, but we should be careful when we say Legendre transformation. It's done with respect to, or performed with respect to, the velocity x dot, right? The x stays intact, but this x dot turns into a momentum. And for simple cases, we know that momenta is just mass times x dot, but we also know, we have done many problems, that when momentum is some complicated function of x dot. Okay, and so then we can calculate dh by dt, right? So that would turn out to be a partial derivative of h with respect to t, and that is same as partial derivative of L with respect to t. So if Lagrangian does not explicitly depend on time, if this is 0, then h is conserved. Okay, so
I have a doubt here.
yeah,
So, in the partial derivative of Lagrangian, wouldn't be there a minus sign because during the legendary transformation there's a minus sign added. So
um,
dh by dt is equal to minus del L by del t.
is it?
I think sir also missed that. I was mentioning that.
Yeah, right. Initial. Let me look at the initial. I think you are correct. Let me just confirm once. You are right. Yeah, this is minus of del L by del T. Okay.
All right.
Yeah. Thanks for pointing it out. Yeah. Okay. So, and remember that h is a function of q and t. Right. Now there is no dependence on t. So what we can do is draw this space of P versus Q. So this is our phase space, and we know that this is some constant E, right? Constant. This constant may not be the actual physical energy, because we need another condition that the velocity should depend. What was the condition? Purval? Yeah, the potential should depend only on the coordinates. So if, but nevertheless, if this Hamiltonian is constant, it means there is a surface on which your trajectory must be. Okay. So overall, we are reducing the dimension of the possibilities of PQ by 1. Okay. So in general, you have a 2n dimensional phase space. So your trajectories would be on 2n minus 1 dimensional um, uh, plane. Okay. So, and the equation of motion for Hamiltonian are q dot is equal to p, right? Which is, sorry, not p, del h by del p, and p dot is equal to minus del h over del q, right? So these are two one order differential equation. If you have n degrees of freedom, 2n, then you put k here. So what we have done is that in Lagrangian equation, the Euler-Lagrangian equation, we had second order equation with k n degrees of freedom. Now we have 2n equations, but with 1 degree, 1 order. Okay. So why is this useful? Because it's easier to, first of all, simulate. Simulation is easier because now you know that how each variable is changing in the next step, right? So you can do Euler method, or there are many Runge-Kutta methods, etc. So all of them are designed basically for first order differential equations. Okay, and there are of course other benefits also. Another is that now our Q and P are on equal footings, right? I can just say Q is minus P. Then I can do certain transformations. So we'll do that in the next week. And we can define our new variables also that might have some good properties that can solve our problems. Okay. So, and the next thing that we did was Liouville's theorem, which just says that if I have a volume element, let's say I have a phase space, and I can start from anywhere, right? So suppose I started from this point and its trajectory is something like this. Okay. Suppose I start from this point. First question is, can it be like this? Answer is no, because they are intersecting. And in phase space, you can never intersect. Why? Because you can look at the point of intersection and ask that if I start from this point, where do I go? And obviously one point has just one future, right? If I drop a pen, whatever happens to the pen, that happens to the pen. There are not like two options that it will either go to left or go down. Okay, so the intersections are not allowed in phase space. So it goes somewhere here, and then I can consider multiple initial conditions, or I can consider a set of closed by initial conditions, a blob, and this blob you can imagine moving in the space as the time evolves. So after some time evolution, the blob becomes something like this. It need not to preserve the shape, right? So uh, and let's say this volume is V1, this volume is V2. What this theorem states is simply V2 is equal to V1, which means the volume of this blob does not increase or decrease, it stays the same. Okay, and the proof was, obviously I'm not going to do all the proof, but what we found was dv by dt was given as integral of gradient of f, and this is initial volume x of t0. Okay, so the system here is considered is x dot, x is a 2n-dimensional vector, is some function of x, and there are 2n such functions, right, for each of the components of x. And so this is your uh, divergence of f. So suppose if I write like this, then f is f1 of entire thing, then f2, etc., right, all the way up to f2n. So the divergence of f is simply with respect to first variable you differentiate f1 plus with respect to second f2, etc., all the way up to 2n. Okay, cool. Or I can just write as dxi fi. Okay, and then second point was that this is 0 for Hamiltonian system, and this means that dv by dt is 0. So the volume element, the magnitude of or absolute volume element does not change. Okay, uh, so I guess that was about it for the recap part. Uh, any questions or comments? If not, by the way, intuitively we can think about the proof by taking a very toy system, which is that x dot is equal to ax and y dot is equal to by. So they are linear and only the proportional terms. Okay, very simple system, and this is obviously very easy to solve, right? What will be x in x as a function of t? That would be x0 times e to the power at. This you can do. Similarly, y of t would be y0 e to the power at. Okay, so now our phase space has two variables x and y. So what it's saying is that suppose y is 0, so on x-axis you start with x0, after some time t you will go to x0 into exponential of at. Okay, this is some time t. Now suppose you start with another x, which I call x1, then you will go to x1 times e to the power at. So suppose this is our delta x, the difference in the initial conditions. Okay, then the delta x as a function of t would be x1 times e to the power at minus x0 e to the power at, which is just delta x 0, let me call it 0, times e to the power at. Okay. Now same way we can think for y0 to y0 e to the power bt, right? This sorry, this should be b. Okay, so what we will get, delta y of t is delta y0 e to the power bt. So now if we start with some x0 y0, and since both of them are evolving independently, we go to some xt yt. Okay, and then we can consider a tiny box around it of dx and dy dimension. Then the volume, so because we are working in two dimensions, the volume is just the area, which is just dx dt. So initial volume is this dx0, sorry, dy0, and after some time t, it is dx of t, dy of t, which is, oh, I was calling it delta, but never, it's same thing, dx0 into exponential of at and dy of t, which is dy0 times exponential of dt. So the new volume is, this was just dv0, right? So e to the power a plus b t. Okay. So the factor by which the volume got increased or decreased is this factor e to the power a plus b t. Okay. And so this a plus b, if you remember, a is x dot over x and b is y dot over y. So this is derivative of this f1, right? This is the f1 function with respect to x. So f1 with respect to x plus f2 with respect to y. This is the number which determines whether k would be less than 1 or plus more than 1. So if a plus b greater than 0, it means k is more than 1, which means volume expands. If a plus b less than 0, means k is less than 1, so volume shrinks. Rather, the blob shrinks, same thing. And when it is exactly equal to 0, k is 1, so volume is constant. Okay, and a plus b is just another name for divergence of f. Okay, so in Hamiltonian case, it is in fact is equal to 0, which means the volume is kept constant. Okay, so of course this is not the proof, this is just to understand. We constructed a very simple linear system. Okay, now let's do some problems. First of all, from the previous year's question, which might be similar to this year's questions. I'm not commenting anything. Okay, so the first one is, suppose a and b are vectors and m is a second rank tensor. Then which of the following are incorrect equations? So the first one is ai is equal to mij bi. This means sum over I mij bi, which is some tensor, but its free index would be j, right? Which is not allowed because on the left hand side we had I. which was the free index. Okay, so this is wrong. So this is incorrect. Okay, second one is AI is equal to MII BI. So again, this means I is being summed over. So there is no free index. This is just a number, scalar, right? So on the other side, we had one free index. So this should have been a vector with a free index I. So again, this is wrong. So this is also wrong. And the third one is AI is equal to epsilon ijk bi. Okay. So since I is being summed over, we have an object which has j and k as free indices. By the way, these indices which are being summed over are also called dummy indices sometimes, especially in relativity, general relativity. Okay, so this is also of course wrong. All three of them are incorrect. Second question is two tensors gamma ijkl. So it is rank 4 tensor and another rank 4 tensors are combined in the following manner. So you have gamma ijkl then contracted with delta lq and then omega q np. What is the rank of above tensor? So as we discussed also in the class that every contraction by delta reduces the rank by 2. So this had rank 4, this also had rank 4. So the overall rank should be 8 if they are just multiplied, but because of the contraction we have two two indices which are being summed over. So overall rank is 6. Okay. You can also think that this L and Q are being summed over. So this is some tensor with free indices I, J, K and M and P. Okay. So just six of them. Okay. So the last one is kind of you have to think a little bit, not mathematical, which is consider rotations in n-dimensional space. If AI and BI are n-dimensional vectors and epsilon I1 In is the Levi-Civita tensor, can you define a vector that would be cross product of vector A and B as we could in three-dimensional space? So they are saying that we have AI and BJ, right? And what we are defining is some new thing, which is combination of I1, I2, etc. up to In, and then we are contracting with A and B. Since A has just one component, let's call it I1, and this is I2. Would this be a vector? And the answer is no, because I1 is contracted with this I1 summed over, and I2 is summed over by this, but we still have uh, so this will be n minus 2 rank tensor, right? Because out of this n indices we summed over two of them and n is greater than 3, right? That is what is given. um, let's just assume that means this is 2 rank tensor or greater than 2 rank tensor, which is not a vector, so that wouldn't be a cross product. Okay, so the answer is no. So I think because it's written just as we could in 3 dimensional, we are assuming that n is greater than 3. Otherwise, of course, we know that we can construct cross product. Okay. Okay, so those were 3 questions. Now let's do some more problems. And since this was mainly a theoretical discussion, mathematical, we don't really have that many problems. I guess they will come in the next class. the physical problems. So I have some basic questions. So the first one is, so what we had in the equation was dv by dt is gradient of f and then d2 x, right? d2n x at 0, right? If given that this is just a number, right? For Hamiltonian it's 0, is some number c, what happens to dimension of volume element? Okay, so the equation would be just dv by dt is equal to, since this is constant, we can take it out, c, and this integral is just the volume. Okay, so then we have 1 over v dv by dt is equal to c, and then we can integrate dv over v is c dt, so ln v is equal to ct, right? So ln v over v0, right? So v is v0 e to the power ct. Okay, so when we start with v0, it will either exponentially increase or exponentially decrease if it is negative, or if c is 0, then it will stay the same, which we saw earlier, right? So if c greater than 0, then v tends to infinity. So that is like we are pumping the energy into system, right? So c can be thought of as rate of pumping energy. So obviously the volume element becomes larger and larger as t tends to infinity. If c is equal to 0, then v just stays as v0. Okay, and if c is less than 0, then volume tends to 0. Okay, this was not the question. The question was what happens to the dimension of volume element. So when we started, if we were in three-dimensional phase space, then if the volume is some finite thing, it has to be a 3D object, right? Only 3D object would have finite volume. So say phase space is 3D. Then volume tending to 0 means it cannot have a finite volume. So what could be the shape? So the dimension has to be less than 3, right? What does it mean? Does it mean that dimension is 0 or 1 or 2? Is it true? First of all, what does dimension 0 mean? It means just a point, right? 1 would mean that it's a curve, and 2 would mean it's a surface, 2D surface. Okay, it means if we start with some 3D blob, it either everything shrinks to a point or a curve in the phase space, or it's a surface, infinite surface, right? But as it turns out, there is another possibility also, which is that it can have fractional dimension, which is super weird because in general we think that dimension is uh, an integer, right? But there are objects called fractals which have fractional dimension, and as it turns out, there are cases when this phase space goes to one of those fractals. Okay, so and that is called chaos. So eventual trajectory belongs to some fractal attractor. Fractal attractor. Okay, we will cover one of that in the next problem. So uh, let's just do that problem, which is called the Lorentz system. You might have heard of it, or you might not have. The first time you hear it, it just blows your mind. Okay, so the system was developed by Lorentz. He was trying to see how can you uh, simplify the equations that govern the weather system. So he could write an equation of this form, in which there are 3 degrees of freedom, or phase space is 3 dimension. Okay, then y dot is x times rho minus z minus y, and z dot is xy minus beta z. Okay, so this x, y, and z correspond to some thermodynamic overall variables like temperature, pressure, etc. I don't remember exactly, and all these sigma, rho, and beta are the parameters of the system. So now we have x, y, z, and the question is, I start some initial conditions in this volume element, what will happen to them? So again, our function f is basically this thing, sigma y minus x rho minus z minus y, and xy minus beta z. So we know the factor by which the volume is shrinking, the exponential rate, what we called it c, which is just gradient of f. So the first term would be with respect to x, second term is f2 with respect to y, and the third is f3 with respect to z. So this is our f1, f2, and f3. So this you can clearly calculate. This is just minus sigma. f2 with respect to y is just minus 1, and f3 with respect to z is minus beta. And these parameters are positive, which means this is negative and constant, right? That means the volume element shrinks. And if you simulate the trajectories, what happens in the end is you get a weird shape that looks like a butterfly. I might have simulations in my laptop. I'll try to show you, and that is the fractal that I was talking about. So this is called Lorentz attractor, and the key thing for attractor is that it is fractal and it is aperiodic. So if you look at just x, the series does not repeat. It it looks like it's a random noisy signal, except that it is not. If you start again from this point, it is deterministic. Nevertheless, it is aperiodic. Okay, so that was something that I wanted to tell you. And the last question is, uh, a potential is given in 1D u of x. Then what happens to So volume. Okay. So of course, if you have paid attention, you know that if the potential is given, which is just a position function of its position, then the system is Hamiltonian. So the volume should not change, but we can explicitly calculate. So what would be the Hamiltonian's equation? So x dot would be v, and v dot would be minus 1 over m gradient of u, right? So del u by del x. Okay, and then divergence of f would be with respect to x, you should differentiate the first function. So del v by del x and minus 1 over m with respect to the second function. With respect to v, we should have second function. This is obviously 0 because v and x are treated as independent variable. So, and since this is partial derivative, this is 0. And again, since u is a function of x, this derivative is also a function of x, some function of x, right? So derivative with respect to v is 0. So this is 0, which means the volume is constant, which means there cannot be, it cannot go to a fixed point where all the trajectories end up there, right? There must be a surface on which these trajectories keep on revolving. Okay, so let's end the discussion here. Let me quickly try to show you the Lorentz attractor if I can. Not audible? Am I audible or not?
Audible, sir.
Audible, no? Okay. Okay, sorry if it was not audible in between. So let me open that code. This is in MATLAB. Lawrence. Yeah, okay. So these are two trajectories in the XYZ volume, XYZ axis. So as you can see, it just revolves around the point. Okay. And then it goes to another wing of the butterfly. So it looks like a double scroll. It's called double scroll attractors. So there are two scrolls. So a trajectory would revolve around for some time and then here for some time, but it's not periodic. So sometimes it does 3 revolutions and goes to there, and here does 7 revolutions, comes to here, 2 revolutions, and overall it looks very planar. You can see this wing is almost plane. The second wing is also plane, but at a different orientation. Yeah. So this is your Lorentz attractor. So its dimension is, as you can imagine, very close to 2, but slightly higher than 2. So it's around 2.006. There are methods to calculate these dimensions, and overall it makes this very beautiful shapes, and that is your Lorentz attractor. Okay. Let me stop it. Okay, so any questions, comments, feedback? Okay, if not, then we'll meet in the next session, and I'll announce the session on. I'll tell the NPTEL guys that I want a session 1 or 2 hours, and I think they will announce it in your portal. Okay, so let's meet next. Okay, cool. Thank you. Bye bye.